So in this lecture, in this short video lecture, I'm going to talk about contracts. And contracts, I'm going to start with assertions, pre and post conditions. Now what's an assertion? An assertion is a statement that's either true or false. So it's a Boolean expression that we are trying to assert. Like for example, you can say I want to try to assert that x is greater than or equal to 0 right here. So we may require that x to be greater than or equal to 0 and as an assertion here. A precondition for a function, for example, we may say that we require at this point the y to be greater than or equal to 0. So we make sure that the precondition is met so that function will not have undesirable outcomes. The post condition means that we ensures that some condition has come true at the end of this function. So there are three things that are important: assertions, preconditions, and post conditions. Now loops are really important things in programming. We write a loop to iterate over a set of statements again and again and again. Now one of the things we need to assure that the loop will terminate, and also the loop will produce the desired output. These two things are really, really important. Now, so in order to get there, we will start with a concept called a loop invariant. So what is a loop invariant? A loop invariant is a Boolean statement that is true at the start of the loop, that's true one time in the beginning, and then at the end of each iteration. This means that the loop invariant must be true immediately after you exit the loop. So why do we study loop invariants? We study loop invariants to probe properties of loops, and that will allow us to prove the partial correctness of loops and what the loops will produce, what the outcome is. And here's an example. So let's take this simple loop as an example. Let's try to define some Boolean statements that may or may not be true as a loop invariant. So we can take a very trivial one, says 1 equals 1, which is a loop invariant because it never changes inside the loop. So that's great, but it is kind of useless. If you take some statement like I equals I, which is also true inside the loop because I is part of the loop, but again it's a trivial statement, therefore although it is a loop invariant, but they are not really useful. If you take a statement like I is strictly less than n, is that a loop invariant? Let's try to see that. We know that when we start I is equal to 0. So if we assume that n is strictly greater than 0 to begin with, this condition is true. What about after one iteration? So I prime is I plus 1. Can we prove that I plus 1 is strictly less than n? The answer is no. Therefore this is not a loop invariant. What if I say I is less than or equal to n? Well, I should be able to prove this now because in the beginning I is 0. If I assume n is greater than or equal to 0 as a precondition, then I know this statement to be true. And the I prime, which is equal to I plus 1, is now less than or equal to n since I is strictly less than n. So we did find a loop invariant called I less than or equal to n. Now if I take the loop invariant I is less than or equal to n, which I know is true here outside of the loop, and also the loop exit condition, which says I is greater than or equal to n, I can conclude that at the end of this loop I must be equal to n. Now how do we find a loop invariant? Now this is a process that may take a while, so let's think about this piece of code. Now we do not know what this does. It's some piece of code that is doing something. Now obviously we can use something like coin to figure out, given x, we can find, maybe we can do a few explorations. What is g of 0? What is g of 1? What is g of 2? And so on. We can do that, but that doesn't give us a loop invariant. That may give us a hint about what this function produces. So to find a loop invariant, we have to come up with a statement, a Boolean statement, that involves I, j, and k perhaps, to come up with a statement that we can prove. So there are 4 things in this piece of code: x, I, j, and k. Now we do know that x is a loop invariant because x never changes inside the loop. Let's start with x